Welcome, everyone. Andy will be talking about the chiral, the Rham complex of Calabi-Yau and hyperkahler manifolds. Feel free to start whenever you're ready, Andy.
Okay, so thanks everyone for coming. And I also want to thank Floor for doing such a great job organizing this seminar this year and last year. It's been excellent, and I've learned a lot from the talks. Okay, so I'm going to talk about the chiral Rham complex, and this is mostly an exposition of Violin's work over the last many years. So there's only a little bit of it that is our joint work. It's really, this is Violin's story. So what I'll do is I'll first remind you what the chiral Rham complex is, then I can state the main results. And then there are two separate steps in the proof. One of them is a reduction to a problem in algebraic geometry, which is the invariant theory of arc spaces. And then the second step is well, after this reduction, then there's something that one has to prove about arc spaces, which is the analog of the fundamental theorem of invariant theory for the symplectic group and the special linear group. Okay, so the chiral Rham complex is locally certain free field algebra called a BC beta gamma system. So let me just remind you what this is and fix the notation. So V is a vector space of dimension D. The beta gamma system is a vertex algebra that you can attach to this vector space, which has even generators, beta x and gamma x prime. So these are linear in V. So I don't choose a basis, but B, that means that bx plus by equals bx plus y. And same thing for the gammas. And they satisfy some OPE. So the betas commute, the gammas commute, and the interaction of beta and gamma is just the first order pole, which is the pairing between V and V star. So I'm going to pick a basis for V and a dual basis. So then this just becomes delta ij, and I'll change my notation. Beta xi will just be beta I, and gamma x prime I will be gamma I. Okay, so there are different choices of conformal vector, but for the moment, let me pick the standard one where the central charge is 2D and beta and gamma are primary of weights 1 and 0. So later we'll see that it's a good idea to change this. For the moment, let me choose this one. Okay, so as a vector space, this beta gamma system is just the symmetric algebra on a bunch of copies of V and V star. So each Vn is isomorphic to V, and this just means the nth derivatives of the betas, and V star n is the nth derivatives of the gammas. Okay, so the BC system is similar, except that the generators are odd. So again, this is attached to V. Bx and Cx prime will be the generators. They have OBEs that look the same, except that they're odd. And as before, I'll pick a basis. Bxi will be Bi, Cx prime I will be Ci. And this also has a standard conformal vector where the central charge is minus 2D. And Bi and Ci are primary weights 1 and 0. And as vector space, this is isomorphic to exterior algebra on a lot of copies of V and V star. Okay, so W will be the tensor product, beta gamma system tensored with the BC system. And I'm going to give it the conformal vector, which is just the sum, the diagonal vector, which has central charge 0. Okay, so I want to interpret these fields geometrically. So the interpretation is that gamma I will be a coordinate function on V star. So this will just get identified with the x prime I. Ci will be the coordinate one form, dxi on V. Beta I will correspond to the coordinate vector field, ddxi. And Bi will be the odd vector field or the contraction with respect to this vector field, iota ddxi. This operates on forms by lowering the form degree by 1. Okay, so I haven't changed anything yet. These are just how I choose to interpret them now. And now what I want to do is make this W bigger by throwing in all the holomorphic functions. So let's say that U is now a coordinate open set in some manifold, some complex manifold, and x1 prime through xd prime are my local coordinates. So these local coordinates, I'm just going to identify with these gammas. And I'm going to tensor W, this vertex algebra that I had, with the ring of holomorphic functions O of U. I'm tensoring over the polynomial ring. So these polynomials are in W, but I can also think of them here. Okay, so the first thing I need to do is explain how this naturally has a vertex algebra structure. So the W is already a vertex algebra. So each of the functions f in O of U I want to have a field that corresponds to these such Fs. So I can naturally make a vertex algebra structure where each F gets a field. The derivative of F is identified with this object. It's the sum of df d gamma I. This is another function, but I think of it now as the corresponding field. This del means ddz in the vertex algebra, where this is just the usual partial differentiation in my ring of functions. So it's the product of these two. This is the derivative. This is an element of W. This is a function. I also have to identify the product of two functions with the normal ordered product of the corresponding fields. And also the identity function I have to identify with the vacuum. If I make just these identifications, you can take some large object and then quotient by those, then I get the desired vertex algebra. And there are certain OPEs that are satisfied. So this beta, which was the vector field ddxi, when it acts on a function, I have this OPE. It just acts by the derivative. B commutes with F because contraction of a vector field acts trivially on functions. And also C is a one form. This also commutes with the functions, or super commutes. Okay, so this is my OPE algebra in this larger object O of U. So now I have to consider what happens under coordinate changes. So let's say that I have another set of coordinates on U, gamma 1 tilde through gamma d tilde. And I have some changes of coordinates. So gamma I tilde is some function, fi of gamma 1 through gamma d. And then this is the inverse change of coordinates. Gamma I is some function gi of the tilde coordinates. So you can ask what happens to these fields. And so ci is a one form. This is the usual way that one forms transform. So this just means the normal ordered product of this function times this field. And I don't even need normal ordered products because these commute. I'm just writing it that way. And also derivative of gamma I transforms as a one form. Bi transforms as a vector field. This is the usual transformation rule for vector fields. And beta I, there's a slight subtlety that this is the term which is the typical rule for transformations of vector fields, but then there's a correction that's necessary for this to give rise to a homomorphism of vertex algebras. Okay, so these are how they transform, and the main theorem of Malakov, Shechtman, and Weintraub from the paper where they introduced this structure is that this change of variables is induces a homomorphism of vertex algebras. If you write down OPEs of these, it's the same. And this is compatible with compositions, so this defines a sheaf of vertex algebras on M. And this sheaf has a conformal weight grading. So that Virasoro element that I wrote down before is a Virasoro element here. At least it gives you this grading. And it's a grading by the non-negative integers such that the conformal weight 0 part is the super polynomial ring on the functions, and well, the gammas, the c's, the one forms, and then all the functions. So this is the usual de Rham complex, just the differential forms on M. There's one thing which is maybe subtle that I'll point out over here, which is that so let's say that OM is the sheaf of homomorphic functions on M. The thing that's a little bit subtle is that this, even though it contains the functions, it's not actually a sheaf of OM modules with respect to the product that I have defined. So if I take an open set and I take two functions and I take a section alpha over U, then I can multiply by taking normal order product with a function. But if I do G times alpha and then multiply by F, that's not the same thing as FG times alpha because of the non-associativity of vertex algebras. So even though this is not exactly a sheaf of modules, it has a filtration such that the associated graded object is the sheaf of sections of this vector bundle. So it's a symmetric powers of a bunch of copies of the tangent bundle and cotangent bundle tensored with exterior algebra on a lot of copies of tangent and cotangent bundle. Okay, so now there's certain global sections that are written down in the original paper of Malakov, Shechtman, Weintraub. So let me talk about these first. So first of all, let me write down some fields and local coordinates. So L is the same Virasoro field that I wrote down before. This is the Virasoro for the beta gamma system. This is the BC system. This is in W, but I think of this now as a local element, a local section of the chiral de Rham complex in local coordinates. Okay, then I can write down this field J. So this generates a Heisenberg field. This is just the sum of BI, CI. And then Q is the sum of beta ICI, and G is BI derivative of gamma I. So these are some things I can write down in local coordinates. And now what I can do is, I want to know whether these give rise to global sections. So I try to write down the same things in the new variables. And then I use my change of variables to rewrite them in terms of the original variables and then compare, see what I get. So if I do this procedure for L tilde, so I write down the same thing with the tildes and then I replace the tilde fields with the non-tilde fields, I get exactly L back. If I do this for J, then J tilde is J plus a correction. It's the derivative of some function. This del is ddz. And this, and same thing for Q tilde. It's Q plus a correction. And then G tilde turns out to be the same thing as G. Okay, so the things that you can observe here are that these corrections are total derivatives. So they don't affect the zero modes of J tilde and Q tilde. And also, if the first Chern class of the tangent bundle is zero, then those corrections are gone. And then these fields are globally defined. So J and G are always globally defined. Sorry, L and G are always globally defined. J and Q are globally defined when C1 of the tangent bundle is zero, but their zero modes are always defined. And some other computations that appear in the original papers are that this Q this was the sum of beta ICI. So this plays the role of the de Rham differential. And when you restrict it to the degree zero, weight zero component, you get exactly the de Rham differential. And also the G1, well, G was globally defined. This one mode is globally defined. This plays the role of a contracting homotopy for Q0. So this bracket is L1. So this tells you that everything beyond conformal weight zero is cohomologically trivial. So this embedding of the conformal weight zero piece in the chiral de Rham complex is a quasi-isomorphism. Okay, so this is all I want to say about the general setting. So from now on, I want to assume that C1 of the tangent bundle is zero, so that in particular, all four of these fields are globally defined. And I want to make a change of variables. So I'm going to replace L with L plus 1/2 derivative of J. So I can do this now because J is defined. And so this is a new Virasoro field where the central charge is not zero anymore, but it's 3D, D being the dimension of the manifold. And also I've changed the conformal weights of betas and gammas. So they now have conformal weight 1/2 each of them rather than 1 and 0. I'm sorry, let me take this back. Betas and gammas have not changed. BI and CI, I've changed the conformal weight. Those are now both 1/2 with respect to T. Okay, so these four fields, it's easy to check, and this is well known that they generate the n equals 2 superconformal algebra with central charge 3D. And in fact, it's the simple one that they generate. So this is a non-generic level, but this is actually the simple quotient that they generate. Okay, so now suppose that the manifold is a Calabi-Yau manifold. So in particular, it has a non-vanishing holomorphic volume form, omega 0. So let me choose local coordinates, gamma 1 through gamma d, such that locally this volume form looks like d gamma 1 wedged through d gamma d. So now that I have this, in these coordinates, there's some extra fields that I can at least locally write down. So I can write down these d gammas are, in my notation, the C's. So C1 through CD is exactly this object. There's also the same type of thing where I replace C's with B's. And then I can take these two fields and apply I can apply Q0 to this field D, and I get one more field. And I can apply G0 to this field E, and I get another field. Okay, so now I have 8 fields. So this is also a well-known fact that these 8 fields close under OPE. They close non-linearly, and they generate some vertex algebra. These D and E, remember that I changed the conformal gradings so B's and C's have weight 1/2. So these are both conformal weight D over 2. And then these things are one more than, these things are 1/2 more than that. So these guys have weight D over 2. These two fields have weight D plus 1 over 2. And this is a vertex algebra that was originally studied by Odaki in the 80s. And there's a non-trivial result of Ilwani, Ekstrom, Callan, and Zebzine from 2013, which is that these 8 fields actually give rise to global sections of the chiral Rham complex. So that in particular, this algebra of global sections contains this thing that I call V0. And they studied in particular the case D equals 3. And this one was the one that they called the Odaki algebra. But I think that for all D, this algebra was considered in Odaki's paper. And it's actually a fact that this VO is a simple vertex algebra for all D due to Bailin. Okay, so now suppose that that D is even and M is a hyperkahler manifold. So in particular, it has a holomorphic symplectic form, omega 1. And again, I can choose nice local coordinates. So this has a nice form. So let me choose local coordinates gamma 1 through gamma 2L, so that the restriction of this form on this open set in local coordinates, it looks like this. So this is a standard form for it. And again, there are 4 sections that I can write down. So this E prime is exactly this form where I replace the D gammas with the C's. I can also replace them with B's, and then I can apply Q0 to D prime, and I can apply G0 to E. So I again get 4 more fields. These also close under OPE. And now what they generate is the small n equals 4 superconformal algebra with central charge 3D. And again, this turns out to be the simple one for all D. And another result of Raimondo and Benzvi and Chesney from 2008 is that for hyperkahler manifolds, these all give rise to global sections. And this B1 is a subalgebra of the chiral Rham complex. Okay, so I didn't write down, I only wrote these in global coordinates, but in their papers, they have other descriptions of these global sections. Okay, so the main result is the exhaustiveness, that those algebras are actually the full global section algebras. Well, so the statement is that if M is a compact D-dimensional Calabi-Yau manifold with holonomy group SUD, then the full global section algebra is this B0, this Odaki algebra. In particular, it's a simple algebra. And if M is a compact hyperkahler manifold of dimension 2L with holonomy group SPL, then its global section algebra is this V1, which is the n equals 4 superconformal algebra. So in particular, this global section algebra depends only on the dimension of M in the holonomy group. Okay, so there are 2 more or less independent steps in the proof. The first step is to show that the algebra of global sections is isomorphic to a certain free field algebra. It's isomorphic to a certain subalgebra of W. W is the BC beta gamma system of rank D, which is invariant under a certain infinite dimensional realgebra of Cartan type. This is the analog of a classical result that the global section algebra is isomorphic to the holonomy group invariance in the fiber for certain bundles that are built from the tangent and cotangent bundle. And then the second part is analyzing this invariant subalgebra of the beta gamma system. And this can be reduced to a certain problem involving the invariant theory of arc spaces. Okay. So step 1 is carried out in a previous paper of Bailin that appeared recently in Communication of Mathematical Physics. And so the sheaf cohomology of the M with coefficients in chiral Rham complex is called the chiral Hodge homology, and the global section algebra is just H0. So what he does is he thinks of M as a smooth 2D dimensional real manifold. And so I'm going to have different notation for the smooth chiral Rham complex. This omega chiral smooth means this larger object, which contains the holomorphic version as a subsheaf, and it also has the complex conjugate as a subsheaf. And so there are some anti-holomorphic fields. The original ones that I had, L, G, Q, and J, that generate the n equals 2 structure are the holomorphic ones, and then these are the anti-holomorphic ones that they commute with the holomorphic ones. Okay, so the smooth complex has now a bigrading with respect to certain modes coming from the anti-holomorphic fields. So the L1, so this notation means the grading operator. L, what we normally write as L sub 0. This acts by K times the identity on this piece, and this Heisenberg field in this anti-holomorphic sector acts by L times the identity in this sector. And this smooth complex you can write as the sum of the KL graded pieces. Okay, so now what I want to do is isolate the part of conformal weight 0 with respect to L bar. So omega chiral L is going to be this piece where the first entry is a 0, the eigenvalue of L bar. And then I take the direct sum of these. That's omega chiral star. And so I have so let me define the del bar operator, Q bar 0, to be, I take Q bar 0 and I restrict it to the subcomplex. So this is a subcomplex with respect to this Q bar 0. And the same calculation that I mentioned earlier says that this, well, Q bar 0 bracket G bar 1 is L1 bar. So this also is a contracting homotopy. And so the inclusion of this subcomplex, where this K component is 0 and this larger thing is a quasi-isomorphism. Okay, and so Linshaw shows that this del bar cohomology of this subcomplex actually computes the chiral Hodge homology for that. Okay, so one step is this statement that there's now a complex that computes this chiral Hodge homology. And the next statement is that the H0 is invariant under certain infinite dimensional Lie algebra in the fiber. So let me try to explain what this looks like. So for any vector space, I can talk about the Lie algebra of algebraic vector fields on V. So these are things like the sum of Pi. Pi is some polynomial in the linear functions on V times ddxi. So if I choose a basis, then the algebraic vector fields look like this. They're closed under brackets. So this is some large infinite dimensional Lie algebra. And one can now consider subalgebras that preserve some differential form. So if I take say a K form, there's the Lie subalgebra that, well, preserving means annihilating in the sense of invariance. So the ones that annihilate this form, that's a Lie subalgebra. So I'll denote this by VW, V omega. Now, given a global section and a point, I can restrict the global section to the fiber, and I get an element of W. W is the BC beta gamma system on some vector space. What is the vector space? It's the tangent bundle at this point. So this is a BC beta gamma system of rank D. And the statement is that if M is a compact D-dimensional Calabi-Yau manifold with Calabi group SUD, then the H0 of M, the global section algebra, is isomorphic to the W invariance, the invariance in W under this Lie algebra of, these are Lie algebras of Cartan type. It's the ones that preserve the volume form restricted to this point. And there's a similar statement for hyperkahler manifolds. The global section algebra is the invariance in W with respect to this Lie algebra of Cartan type, where the form omega 1, the homomorphic symplectic form, is preserved. Okay, so then the problem now is reduced to understanding the structure of these invariant spaces. And these are very large Lie algebras. So first observation is that by virtue of being invariant under these large Lie algebras, we can throw out the gammas. We need to keep betas derivatives of gammas, B's and C's, but the gammas are immediately thrown out. So I give this a name. W plus just means the subalgebra where I throw out the gammas. And notice that if I throw out the gammas, the betas and the del gammas just form Heisenberg algebra of rank 2D. Okay, so the next observation is that this is now the Calabi-Yau case. This Lie algebra of Cartan type contains a Lie subalgebra, which looks like this half of an affine Lie algebra. So SLD adjoint T. So this is just polynomials with SLD coefficients in the variable T. This is a Lie subalgebra. And moreover, the invariance in W with respect to this very large Lie algebra, if I take just W plus and I take only the invariance under SLDT, that's the same thing. These are isomorphic. And similarly for the hyperkahler case, taking the invariance in W of this much larger Lie algebra is the same thing as taking the W plus invariance under SPLT. SPLT is again a Lie subalgebra of this Lie algebra of Cartan type. Okay, so now we reduce to finding the invariance in this free field algebra under a Lie algebra of this form. And this problem can in turn be reduced to an associated graded version of the problem. So when I tested the associated graded, the graded algebra of W plus is a symmetric algebra on a bunch of copies of C and CD. Each of these CNs is for each n, these are all CD, CD star. So symmetric algebra on this vector space plus its dual, tensor symmetric algebra on this vector space plus its dual. Okay, and so once I've passed to the associated graded version of the problem, this is naturally, well, these Lie algebras, well, I maybe have to pass to a completion. They become the Lie algebras of the arc space of corresponding Lie group. So in the Calabi-Yau case, it's SLD. In the hyperkahler case, it's SPL. So finding the invariance under these Lie algebras is the same thing as finding the invariance under the action of the arc space of G on rings of this kind. Okay. So this problem is now in the ballpark of invariant theory of arc spaces. So I'm going to say a little bit about this. And this, I actually talked about this in my talk a while ago in a different context, but it's a while ago, so I'll repeat some of what I said before. So so this is a construction in algebraic geometry that you begin with a scheme, and I don't have to work with C, but in this setting, it suffices to work with C. So X is some scheme of finite type over C. There's another scheme, X infinity, that's called the arc space of X, that can be characterized by its functor of points. So if you have a commutative ring, the A value points of X infinity are in bijection with the A of T value points of X. This construction is from this definition is obviously functorial. If you have a morphism of schemes, you get a morphism of the corresponding arc spaces. And if X happens to be affine, then there's a nice presentation for X infinity. It's also an affine scheme. So suppose that X is a polynomial ring in some variables x1 through xn, mod some ideal with some finite generating set. So R would be this ring, X would be spec R. So C valued points of X infinity are supposed to be C of T valued points of X. So a C of T valued point of X is a morphism from spec C of T to spec of this ring, which is the same thing as a ring homomorphism from this ring R into the power series ring C of T. So how do you characterize such a ring homomorphism? Well, each generator corresponds to some series, and the series have to satisfy the defining relations. So for each generator x1 through xn, phi of xi will be some series. So I write it, I give it the name to some coefficients, xi0 plus xi1t, etc. And because this is a homomorphism, when I plug the images into each of the generators for the defining ideal, this has to be 0. And the way I interpret this is I collect like powers of t, and then this will be some equation in finitely many of these variables. And so these coefficients, xij for j running from 0, 1, 2, etc., I think of them now as coordinate functions on the arc space. And I can consider the ring of polynomials in these coordinate functions. And this has the derivation that I define by just raising this index. And so you may have seen in other papers, sometimes there's an extra factor of j plus 1. It doesn't matter how you normalize this, but the characteristic 0. So I'm just choosing to do it this way. So D just raises this index I extend it by the Leibniz rule to monomials, and then I extend it linearly to the whole polynomial ring. And so I can apply D and powers of D to the generators of the ideal of relations. So FLR will be the rth derivative of FL. So this is a well-defined polynomial. And then it's not very difficult to check that the requirement that I need for this map to be a ring homomorphism, that all the FLs annihilate the images, that translates to this condition that all the derivatives of the FLs, when I plug in all the variables that can appear, which is all the x's and the derivatives up to the rth one, these are 0. And so this gives me a presentation of the ring of functions on x infinity. X infinity is spec R infinity. R infinity is just the ring of all the polynomials and all the xij's, and then the ideal is all the f's and then all their derivatives. So in particular, these xi's I can identify with xi0. So I can think of R as a sub-ring of R infinity, and R generates R infinity as a differential algebra. Okay, so now let me say something about the interaction between invariant theory and arc spaces. So let me state a problem that's quite general, that's difficult to solve in general, but the setting that we need, it can be solved. Okay, so G is an algebraic group, and V is a, say, finite dimensional G module. So there's an action of the arc space G infinity, which itself is an algebraic group. It's a big unipotent extension of G. This acts on V infinity. And one can consider the categorical quotient V mod mod G. This is a spec of the ring of invariance. So CVG means the ring of G invariant polynomial functions on V. Take spec of that. That's what I mean by V mod mod G. And there's a quotient morphism from V to V mod mod G, which is just dual to the embedding of this CVG in the ring C of V. This induces a morphism of arc spaces, V infinity to V mod mod G infinity. And so there's an induced morphism, V infinity mod mod G infinity to V mod mod G infinity. So what this means actually is that, so V infinity mod mod G infinity means spec of the ring of G infinity invariant functions on V infinity. So that's what this is over here. C V infinity. V infinity is a big flat affine space. So this means the G infinity invariance in this large polynomial algebra. There is a map from the ring of invariance. Well, if I take the ring of invariance and then take the arc space, there's a map in this direction. So this homomorphism is what I'd like to understand. So in general, so this is always you have this homomorphism, but in general, it's neither injective nor surjective. So so how can this fail to be surjective? This can be bigger. You can have more invariance here. And so one setting where this is never surjective is when G is a finite group. So G can be a finite group, then G infinity is still the same finite group. And this thing will always be a lot bigger than the image. The thing on the left is always finitely generated as a differential ring. In particular, it's generated by CVG, which is a finitely generated ring. Whereas this thing on the right is never differentially finitely generated when G is finite and the action is non-trivial. So this can often fail to be surjective. It can also fail to be injective because the ring on the right side is a subring of a polynomial ring. So in particular, it's always an integral domain. But even though V mod mod G can be, V mod mod G can be an integral domain, but when I take its arc space, that can fail to be reduced. This can have no point. Yeah.
Did you just say that if the action of G is finite and it acts non-trivially on the arc space, say just of an affine variety, then the ring of invariance is not finitely differentially generated?
That's right.
So this is, it doesn't matter how simple that action is, as long as it's non-trivial.
As long as it's non-trivial. Yeah. This is in my paper with Jerry and Violin from a long time ago.
Okay.
Even you can even see the example of Z2 acting on the one dimension.
Yeah, that's what I was trying to do now in my head. And
No, it's not finitely generated because what happens is that let's say you take polynomials in one variable, and then you take the arc space, and you have infinitely, now you have this one variable and all its derivatives. So what are the Z2 invariants? Well, they're all the even degree. So that means things of, so it's generated by a quadratic. So if you take like, let's call it x squared, x times second derivative, x times fourth derivative, you need all of those. X times any even degree. Okay, so this can fail to be injective also because this can be a non-reduced scheme. There are examples like that. I'll mention them in a moment. So it turns out actually that if V mod G is an affine space, which is quite rare, but there are interesting examples where it's an affine space, then this map is an isomorphism. And also if this map, if V mod G is a complete intersection, then this is also an isomorphism, but in general it's neither. Okay, so now I want to specialize to the settings that are relevant for this problem. So let's take G is GLN, W is CN, the standard representation. And now let me make a bigger representation V by taking a bunch of copies of W and also a bunch of copies of W star. So P and Q can be arbitrary. Okay, and so the claim is that this map that I defined in general before is always an isomorphism. Okay, so this is a non-trivial statement because, well, when P and Q are small, then V mod G is smooth. I mean, yeah, V mod G is smooth, which means that it's an affine space. So this is already known. But when P and Q are big, then that's not true anymore. There's a few cases that are intermediate where it's a complete intersection, but usually it's neither. So it's not at all clear why such a statement should be true. And so I want to also interpret this as being the analog of the first and second fundamental theorems of invariant theory for GLN in the arc space setting. So what this thing actually says, when I say that this is an isomorphism, the left-hand side, I know what this is. This is just the differential algebra, the sort of free differential algebra generated by the classical ring of invariants. So the classical ring of invariants is well understood by Weil's theorem. The generators are quadratics. They correspond to a pairing of one of the W's and one of the W stars for one choice of here, one choice of here, and the relations are determinants. So first fundamental theorem tells you that the invariants are quadratic. Second fundamental theorem says that the relations are all generated by determinants. But when I say that this is an isomorphism, it also tells you what the G infinity invariants are on V infinity. So this is why I interpret this as the fundamental theorem of invariant theory for arc spaces. The arc space invariants in this big polynomial ring are differentially generated by the classical ones, and all the relations are differentially generated by the classical relations. That's what it means for this to be an isomorphism. So we get both the generators and the relations for the arc space invariants on C of V infinity. Okay, so that's the GLN case. And the SP2N is a similar story, but if W is the standard representation, and then V is a sum of many copies of the standard representation, then this map is always an isomorphism. And so the description is similar for the classical invariant theory for the symplectic group. The generators are quadratic and the relations are Pfaffians. And so what this tells you is that in this setting of, I take the SPN infinity invariance in here, it says that the relations are all generated by derivatives of classical ones. And the relations are generated by derivatives of classical Pfaffians. So again, it gives a description of this arc space invariant. Okay, so the story for SLN is a little bit more complicated. So for SLN, again, the setup is the same. I take n greater than 2, I take SLN, I take CN, and then I take a representation which is many copies of CN and many copies of CN star. So the statement here is that if P and Q are less than or equal to n plus 2, then this is an isomorphism. So it's only true in some range. They both have to be less than or equal to n plus 2. So I think when they're less than or equal to n plus 1, it's either smooth or a complete intersection. There's one more case that's not covered by previous results. But then if one of these is at least n plus 3, this map is surjective, but it's not injective. And so surjective is good enough for our purposes because for what I need is not necessarily the relations here, but the generators. So saying that this is surjective means that this ring of arc space invariants is actually generated by the classical ones of the derivatives. So it gives me generators, but not relations. And so it turns out that, that there are more relations when one of these guys is at least n+3. So there are extra relations, but they can be described explicitly, and they coincide with the nil radical in this ring of invariance. So this is a situation where V mod G infinity is not reduced and it has a nil radical, and the nil radical we can completely describe. And it's actually finitely generated as a differential idea. But for the purpose of this talk, I don't need to understand these relations, only the generators. Okay, unfortunately, the similar results for the orthogonal group are missing. It would be very nice to know results like this for the orthogonal group, but so far the methods don't work. And also for OSP 1,2n. The classical invariant theory is also understood for the standard representation of OSP 1,2n. It would be nice to get some similar results like this, but out of reach at the moment. Okay, so the last thing is that I'd like to extend, so the problem that I had to deal with originally did not just have even variables. Everything so far I've said about the invariant theory of arc space is about arc spaces, the groups of arc spaces of groups acting on polynomial rings. But I also have to be able to deal with odd variables. And so this is typically difficult, but there is a setting where one can do it. Okay, so the general setup, this actually is not as general as what we can do, but it's enough for the purposes of today's talk. So G will be an algebraic group, U will be some finite dimensional G module. And I take the ring of functions on U infinity is just the symmetric algebra on many copies of U. So the nth UN is just the nth derivatives of the generators. If I pick a basis for U star, then take the nth derivatives, I get basis for UN. Again, so D sends U star to U star, the next one. It sends the nth one to the n+1th one. So this thing on the right is a way of writing C of U infinity as a differential algebra. And of course, it's generated by the symmetric algebra on U0 as a differential algebra. So the reason I'm writing it this way is that I can take the exterior analog of this. I can take the exterior algebra on a sum of a bunch of copies of U star, where the differential does the same thing. It raises the n index to the next one, n+1 index. And this is differentially generated by this exterior algebra. So here D is an even differential on this supercommutative ring. And there's an action of G infinity on this big exterior algebra given on generators by exactly the same formula that it's given on symmetric algebra. And so I can also consider the invariance, the G infinity invariance in this symmetric piece as well as the tensor product. And so there's a similar statement. Well, there's a statement that if I take the symmetric algebra on all these UNs, tensor the exterior algebra, and I take G infinity invariance, one thing that's obviously sitting in there is the stuff that comes from U0 and U0 over here. So the stuff that has no derivatives, the G invariant subalgebra will map into this. And then these brackets mean in this notation is the differential algebra generated by this subalgebra. So this may not be everything, but this stuff with no derivatives, G invariant lives in here, and then all the algebra generated by the derivatives lives in here as well. So I have a map. This is some embedding. And so in general, this will not be everything. But there is a hypothesis that guarantees that this is everything, which is the following. If U happens to be a representation with the property that if I take many copies of U, K copies, and I consider this map that I wrote down before. So here I've got a bunch of copies of U. I take this thing mod G, take the arc space, take the ring of functions of that. This maps to the arc space invariance in many copies. Here I take the arc space of this. In general, this is not an isomorphism, but if it is, actually what I should say here is if this is surjective, I only need surjective. If this map is surjective for all K, then these are equal. Okay, so, and that's the case in our main example. So this is a hypothesis that's not often satisfied, but it's satisfied in the case where G is SUD and U is a bunch of copies of the standard plus its dual. And also when G is symplectic and U is just a bunch of copies of the standard representation. So because it's satisfied in those settings, if you go back to the associated graded algebra of W, so I have to go way back now. So we needed to understand the invariance in an algebra of this kind. So what I just explained is that for this particular problem, this will be generated by the stuff with no derivatives, the stuff where these n's are 0. And if you use the description of invariance that comes from Weil's book, either for the SL or for SP, you get exactly the associated grade versions of those 8 fields that I wrote down. Okay, so in the Calabi-Yau case, one of them is the determinant. So the difference between the invariance under SLD and GLT, D is the presence of D by D determinants. That D by D determinant is the thing that corresponds to the volume form. It's actually odd, so it's just a product, but that product of C1 through CD you interpret as a fermionic determinant, and that's given by Weil's theorem. And in the symplectic case, all the invariants are quadratic, and those are the generators for this n=4 superconformal algebra. So at the level of associated graded, you get those 8 generators, and that gives you the generators for the corresponding vertex algebras. Okay, so that's all I wanted to say.
Thank you so much, Andy. That's really cool. Let me stop the recording first.